Some presynaptic neurons have strong synapses with their postsynaptic neurons and produce a significant depolarization. Other neurons have weak synapses and they produce less depolarization. However, those weak synapses can become stronger through a process called associative long-term potentiation. This occurs naturally when neurons fire at the same time as neurons that already have a strong effect. In the laboratory, the researcher uses groups of neurons and isolated neural tissue. In these illustrations, a single neuron represents a group of neurons. First, the research identifies two groups of neurons that have connections to the same group of postsynaptic neurons. Stimulating one group of the presynaptic neurons with a strong electrical stimulus causes a high rate of firing in the postsynaptic neurons. These neurons function as strong synapse neurons. Stimulating the second group of neurons with a weak electrical stimulus produces a lower rate of firing. These are the weak synapse neurons. Next, the researchers stimulate both groups of presynaptic neurons simultaneously, one with the weak electrical stimulus, the other with a strong stimulus. As a result, the formerly weak synapse neurons have become potentiated. Now, stimulation of these neurons with a weak electrical stimulus produces a high rate of postsynaptic firing. Now, think of the strong synapse neurons as the input from an electrical shock to the finger, causing arm flexion and withdrawal of the hand. And think of the weak synapse neurons as input from an auditory tone, which has little or no effect on the postsynaptic neurons and produces no arm flexion. And then imagine pairing the two stimuli, as you would in a classical conditioning experiment. And you can see why some researchers think long-term potentiation is a good explanation for why classical conditioning works.